This is the section 6.3 and 6.4 notes, logarithmic functions and their graphs, page 4. So we are going to talk about logarithmic functions. This first page is a review of exponentials. So remember when we write our basic exponential, we are looking at this form, f of x equals a times b to the x, when where a is our initial value and b is our rate of growth or decay, so our growth or decay factor. And so let's talk about how we write an example when we are given data. So our initial value, remember that is the value at time t equals 0. So our initial value here is 2. The growth or decay factor is how much it takes us to get from one value to the next. So to get from 2 to 8, it's times 4. To get from 8 to 32, it's times 4, times 4, times 4. The other way is to take a value and divide it by its previous value. We want to make sure we get the same thing. So 8 divided by 2 is 4. 32 divided by 8 is 4. 128 divided by 32. When we have real world data, it's not going to be that everything works out nice and neat like this. In a contrived situation, it probably will. So our function here is our initial value times our rate of growth raised to the x power. So take a minute to look at example 2. This would be a great time to pause the recording, take a shot at this on your own, and then unpause, come back, and see how you did. So we have an initial value, A naught, at time t equals 0 at 2,400 grams. It's not really obvious what the growth or decay factor is. Let's see, we'll put growth up here because things are getting bigger. This should be decay because our numbers are getting smaller. So I'm going to go 1,800 divided by 2,400. I get 0.75. 1,350 divided by 1,800, I get 0.75. 1,012 and a half over 1,350, weird. And 759.375 divided by 1012.5. So my decay factor is 0.75. Our rule, and we're just going to call it g of x just so we're different from above. Our initial value is 2,400. Our rate of decay is 0.75 raised to the x power.